Hi everybody, it's been a few months now since I did my last YouTube video due to other family commitments, which meant I have had very little time to spend in my electronics workshop. But as time's freed up, I thought now is the good opportunity to have a look at a fresh project, and today we're going to have a look at designing and building a DC voltage calibrator. Now these units are available in the marketplace. They tend to be quite expensive, ranging from a few £100 to £1,000 or more, and that means that they're normally out of the budget of the hobbyist. So we're going to try and design and build our own today and stick to a budget of around about £50. Now I do have an example of one of these professional units in my workshop, which I actually purchased second hand. It's one from Time Electronics, and this particular unit goes from 0 to 9.9999 of a volt, and it actually even goes down to microvolt ranges as well, but we're not going to achieve that with our project today. We're going to go down to 1 millivolt. Now this particular unit achieves its voltage ranges by a rotary switch, so it does it in 5 ranges, and then it uses 5-digit thumb wheel switches here to set the actual voltage. Now they claim an accuracy for this unit of 0.02%, but when you get down to 100 millivolts or less, that accuracy drops off to around 0.05%. It is also capable of giving 30 milliamps output current maximum, and it has a long-term stability, they claim, of 10 parts per million per hour. So quite a nice little unit, but quite expensive for the hobbyists. So let's have a look first of all at some of our requirements for our project today. Here we see some of the main points of our design today. We're going to have a range of 0 to 10 volts in 1 millivolt steps, which I think will be more than adequate for the hobbyist. We're not going down to the microvolts on our design today. I'm going to match the 30 milliamps maximum output current you find on some of the professional units, but we're going to dispense with any of the switches that you saw on the Time Electronics model I showed you. I'm going to use instead a Tft color display. The one I'm going to use is 2.8 inches, and this particular one has a touchscreen control, so we're going to control everything from the touchscreen. We're going to use standard dual inline pin ICs which are socketed. This will make this design a lot easier for the hobbyist to make. I know in some of my previous projects I've used surface mount ICs, which can be sometimes a little bit more difficult for the hobbyist to use. So we're going to stick with standard dual inline pin ICs on this project today. And we're going to power this unit from a 18 volt DC supply, which can either be a little power pack, mains power pack we can plug in, or we can run it from batteries. You could run it from 2 9-volt batteries, or we can have a look at some lithium batteries which could then be rechargeable. So that's something we'll consider a little later. So let's have a look first of all at the block diagram of our design today. Here we see the block diagram of our project today. I'll just quickly go through first the overview of the operation of our design, and then we'll have a look at the circuit in a little bit more detail. As you see here, we're using the Arduino Nano to control our circuit today. That's going to be used to drive both the user interface, which is the thin film transistor liquid crystal display, which also has a touch screen capability, and also drive the 12-bit DAC, which is going to determine the output reference voltage. For driving the display, we'll be using the 4 lines of the SPI bus, and for driving the 12-bit DAC we'll be using just 3 lines because we only need data coming from the Arduino Nano to drive the 12-bit DAC, and then we have the clock and the chip select line. The output from the 12-bit DAC will then give us our reference voltage, or our programmable reference voltage coming out, and the reference voltage driving the DAC, we're using a 4.096 volt reference, and in this case I'm using the Maxim, the Max 6241 IC, which has an accuracy of plus or minus 0.02%. We have the ability there to provide some trim with a little 10k preset, but in any event the accuracy is quite good without the trim, so that's an option that you can either fit or not, as the case may be. Now, because we're using a 12-bit DAC, I'm using the microchip MCP4922, which is in fact a dual 12-bit DAC. We're only using one of the DACs, the A DAC at the moment for our project, which leaves the other DAC, B DAC, free for future upgrade. As we're using the 12-bit DAC, it means it's got a possibility of 4096 steps effectively. Well, it goes from 0 to 4095, which means that if we're driving it with a 4.096 volt reference, it means for every step coming out of the DAC we have 1 millivolt. So the resolution of this particular circuit is 1 millivolt steps. The output of that is then fed through 2 precision operational amplifiers before going through a logic on-off switch at the output, switch the output on and off before we get the reference voltage there on the output. As we're only using a voltage reference of 4.096 volts, and also the 12-bit DAC is driven from our 5 volt DC supply, the maximum voltage we'll ever be able to get out of this DAC is going to be around 4 volts. That means at our output we could only go as high as 4 volts. But I mentioned earlier that we want to be able to go up to 10 volts. So if the DAC voltage has to go greater than 4, then we have to use some amplification to amplify that reference voltage coming out. If I give you an example where our Arduino Nano, we select on our touch screen a voltage of 6 volts, then that information is fed into the 12-bit DAC, but as we can only get a maximum of 4 volts coming out, then there is an error in our output. So in order to get 6 volts coming out, what we do is the 6 volts that we've set with our Arduino Nano and is displayed, we divide that 6 volts by 2 before driving the 12-bit DAC. So we've got 6 volts which we set with the Arduino Nano. We divide it by 2 within the Arduino Nano software, and then what we get driving the 12-bit DAC is a 3 volt signal. That means that the information coming out of the DAC now will give us 3 volts there, which is generated in 1 millivolt steps. That is now fed into the first precision op amp, and we set the gain of this particular op amp to ×1. In fact, these op amps have the option to have the gain set as 1 or as ×2, and the gain is switched by using these gain switches. I'm using a DG303, it's a Vichy analog switch in an IC package, and that's going to be used to control the gain of this precision op amp, and the same applies there. So if this particular op amp is set as a gain of 1, then we'll get 3 volts coming out there. The next precision op amp we set now to a gain of 2, which means the output coming there is 6 volts, and then when we operate the output switch, the reference voltage out is our 6 volts, which is what we set at the start. If on the other hand we wanted to get up to 10 volts, then let's say we want 10 volts now. Let's also select 10 volts. What we now do within the Arduino Nano, we divide the 10 volts by a factor of 4. So instead of 10 volts coming out, we have 2.5 volts coming out. We're still showing on our display 10 volts of what we've selected. The output from the DAC is now going to be 2.5 volts. What we're now going to do is switch the first op amp to have a gain of 2. This now means the output of that will be 5 volts. We'll also switch the last op amp to have a gain of 2, and that now means that the output voltage there is going to be 10 volts. So in that way, what we can now do is, even though we have a limit in terms of our reference voltage, we can now get up to, or slightly more than 10 volts if we wish, coming out of our DC Voltage Calibrator. And the trick really is to set the drive voltage coming from the Arduino driving the 12-bit DAC in such a way that with the combination of the gains of these precision op amps, we get the correct voltage coming out. Now both of these gain switches are controlled by digital ports from the Arduino Nano. So they're automatically selected dependent on what voltage we select. Now the power supply for our circuit today, here we've got 3 voltage outputs. We need a 5 volt supply to drive the Arduino Nano, the display and the 12-bit DAC. We need a plus 15 volt supply, which I'm going to use to drive the 4.096 volt reference. And then we need a plus 15 and minus 15 volt supply to drive both the gain switches here, the analog switches, and the precision op amps there. Clearly the reason we have to have a higher voltage in this area of the circuit is because we need to get our 10 volts coming out as our maximum voltage. So there's no way we could do that if we were driving these with a 5 volt supply. The power supply design of that circuit is such that I'll be using a DC converter IC, the TC962, which is also a microchip IC. The reason I've selected this one is that it's quite good in terms of it allows us to have a little bit more current supplied. But we'll have a look at that in more detail later. I've also added a DC blocking diode there to the input of the power supply circuit to give us some protection in the event of connecting the 18 volt DC input in reverse. So that gives us some reverse protection. So there we have it. There's our circuit today. I have also made provision on the final circuit for future upgrades, and we will discuss that later. In order to better understand the switching of the gain of the op amps I'm using in the circuit today, I've just drawn up a truth table here just to illustrate the point. I've got the output voltage ranges here that we can select. I've got there the Arduino divider used. What we mean there is that we use software to divide the set voltage, and then here we see the gain of the op amps. I've also made reference to the U5 and U1, which relates to the indications we've got on the schematic diagram, which we'll see later on. So if we choose a voltage between 0 and 4.000 volt, then we don't divide our voltage set, so that stays at 1. We have the first op amp set at a gain of 1, and the second op amp also set at a gain of 1. In reality, the second op amp we're using there will actually just bypass it, so effectively it will be 1, whereas the first op amp will use it as a unity gain buffer. If the voltage is in the range of 4.001 to 8.000, we then divide the input voltage by 2 in software in the Arduino. We set the first op amp to a gain of 1, so it's a unity gain buffer, and we set the second op amp the gain of 2. And then finally, if the voltage is between 8.001 and 10 volts or slightly higher, we divide the input voltage in software by 4, and then we switch both of the op amps to have a gain of times 2. So that just illustrates the arrangement that we'll use when we come to our software for this project today. Now I just quickly want to explain why we've chosen a plus and minus 15 volt supply for our op amps in the output stages. and the reason mainly for that is so we can achieve our 10 volts maximum output at 30 milliamps. Here we can see a graph taken from the INA 105 datasheet, which shows the relationship between the voltage out and the current out with different power supply voltages, plus or minus voltages there. And you can clearly see that if we were to use a supply voltage of plus or minus 12 volts, then we could never actually achieve our 10 volt output. You can see here it would always be below 10 volts, and there you can see it's dropping down to probably around about 8 volts at 30 milliamps. So to achieve our 10 volts output on our op amps, we're using a power supply plus or minus 15 volts, so that's that line there on our graph, and that means that we're well within the ability to achieve our 10 volts there and our 30 milliamps output current there. So that's the reason why we chose that for our supply. We could have chosen a higher one if we wanted, but there was no need, as you can clearly see that the plus or minus 15 volts gives us exactly what we require. So that's just showing you why I chose the plus or minus 15 volts for our INA 105 precision op amplifiers. It's worth just having a quick look at the analog switch ICs that I'm using, the Vichy DG303B. This shows you the internal structure of those ICs. You can see the switching arrangements there. So you've got a switch which is open, a switch which is closed, and that switching can be toggled by the input there going on to pin 6. And you've got an identical switching arrangement there, one switch open, one closed, and again the logic input on pin 9 will simply toggle those switches. So when that one closes between 10 and 11 pins, then 12 and 13 will open, and you have the same effect here on the other side. So that's the type of analog switch that we're going to use in our circuit today. Well, it's worth just having a quick look at the internal architecture of the 12-bit DAC we're using on our project today. I'm using the microchip MCP4922, that's the 12-bit version. The other two model numbers there are for the 10 and the 8-bit versions. And the interesting point I want to show here is, first of all, there is two DACs inside this chip. We're only using this half in our project today, the DAC A, and DAC B we may use as a future upgrade later. So let's just consider what happens when we feed our information into the DAC via the SPI bus there at the top. So you've got the data and the clock signals going in there. When the chip select pin to the DAC goes low, the information from the Arduino is read into this logic interface here. And then when the chip select pin goes high, the information is then latched into the input register. So now we can remove the data coming in. So we don't have to keep supplying this DAC with data on the SPI bus. Once we've got the data for the voltage, it's latched into the register there, in our case the A register. And that happens when the chip select pin then goes high. Now that's useful for us because it means we don't have to keep in our program loop going back and saying write to DAC, write to DAC. We only need to write to the DAC if we want to change the voltage, and we only need to write to it once when the voltage changes. This particular DAC has got a dual buffer registered here on the input. The reason for that is that you'll see we've got another connection there, the LDAC connection there, and that allows us, if we're using the dual DACs, to latch the outputs at the same time. In our particular case, we're not using that today. We're just supplying the register output there from the A input register to the DAC register there straight through. That's then going to the DAC string there, which we supply with a voltage reference. That's our 4.096 volt reference. You have also the ability to put a alternative reference for the B DAC, and again we'll look at that maybe later. The output then comes through the output amplifier there before arriving here on the Vout A pin. Now there is an ability also in the DAC to alter the gain of that, I think by a factor of 2, so you could actually amplify it by 2 on the output stage of the DAC. But again, in this part of the project today we're not using that, but it may be something to consider at a later stage. So that's our 12-bit DAC. Here we see the TFT display, the colour display we'll be using for our project today. This particular one I'm using is a 2.8 inch version. It comes also with a touchscreen capability, and it uses the Ilitech ILI 9340 chip interface for driving the display. Now this particular one comes on a, as you see there, on a printed circuit board, which also has on it the ability for an SD card as well, which we're not using at the moment for the project, but I'll just turn it around and we'll have a look. And let me just zoom in a little bit closer. Here we now have a closer view of the back of the TFT display, and what you'll see here is there's the SD card with the pin connections there for reading it. So we're not using that at the moment. These are the connections that we'll be using on our project, and this particular module comes already with these pins soldered on, which is quite nice. Now, although the display unit itself operates at 3.3 volts, interestingly there is actually a little voltage regulator chip there on the PCB, so we can supply it with a 5 volt supply. You'll also notice that on the PCB there's a little link just next to the regulator chip there, and if that link is left open then it's using the regulator IC on the board. If you close that link, then it all operates at 3.3 volts. Now, although I say that the regulator will allow us to feed it with a 5 volt supply, which we will do, I'm not too sure with regard to the data signals going to the display. They may still be at 3.3 volts, so we may have to just put some limitation on the driving voltage going to the display, and I'll show you how we do that on the circuit. So there we are, that's the display module for the project today. It's just worth having a quick look at the INA 105 and how it does our gain switching today. The IC itself is a precision op amp, and it's got laser trimmed resistors actually on the silicon chip itself, all of which are 25k, and it's a case of how we connect those determines the gain of the op amp. Now, our configuration today is such that we have pins 5 and 6 connected together, that's our output there, and we have 1 and 3 connected together, which is our input. The only pin we're going to switch is going to be pin 2. And the configuration on this IC is that if we flick the switch of pin 2 to the top position there, that gives us a gain of ×1. And if we switch it to ground, we get a gain of ×2. So all we need to do in our circuit today is simply have a switching arrangement that simply switches pin 2 either to ground or to join with 5 and 6, and that'll give us either ×1 or ×2 gain. So it's quite simple, and that's the circuit that we'll be using today. Here we now see the full schematic for our project today, so I'll just quickly walk you through this. The power supply arrangement is there, top left hand corner, and we're feeding that with an external 18 volt DC supply, and I'm achieving that by using one of these little plug-in mains adapters. This is giving me 18 volts DC at up to 2 amps, more than our requirements today. At a later stage what we will do is we'll look at having a battery option as well. Now the voltage going in is then fed through a DC blocking diode, and that gives some protection in the event of the input supply being in reverse. It's now feeding a 15 volt fixed regulator IC, so we're getting 15 volts DC there. That 15 volt is then feeding a 5 volt regulator IC, giving us a +5 volt supply, which is then feeding the Arduino Nano, the TFT display and the 12-bit DAC. The The rest of the circuitry you'll see on the board here is mainly coming from the plus 15 volt supply. Now that 15 volt supply, we're also feeding it to a DC voltage converter IC, which is a charge pump IC, because we need to generate a negative voltage. So we want to convert the plus 15 volts to a negative 15 volts, and that's achieved with U3, which is a microchip TC962. And the reason I chose that is because of its additional current handling capabilities. This can give us up to 80 milliamps output current if need be. Not that we need that today, but maybe for future upgrades we may need to rely on some extra current. So we've got a negative voltage coming out there on pin 5, and just to ensure that it's properly regulated, I've stuck another voltage fixed regulator there, a negative 15 volt regulator IC. So then what we're getting out there is a minus 15 volts. Now we'll see how this works. It could well be that if our 15 volt negative there is a little bit low, we may have to supply the DC converter directly from the 18 volt supply coming in, but we can have a look at that as we look at the final project. So we've got our negative 15 volt supply there, our plus 15 volt supply there, and that's what's used to feed the other ICs in this schematic. The 15 volt supply is also feeding the voltage reference IC here, U10. That's using a MAX 6241, which has an initial accuracy of plus or minus 0.02%, and also has some ability to be trimmed on the voltage output. The other option you have is to go for the MAX 6341, which has got the same accuracy of 0.02%, but it has a better long-term temperature coefficient. But for that you need to pay 3 times the price. So I think maybe for this project the cheaper version, the MAX 6241, is probably adequate. But the choice is yours. And the output of that, as I say, can be trimmed with a little 10k preset, so we can trim that to plus 4.096 volts for any calibration we need to do later. Now the reference voltage from that is what we feed into our digital analog converter IC, U9, so that's the voltage going into VREF-A, and as I mentioned earlier, we're only using half of this dual DAC, 12-bit DAC. We're using the A part of the DAC, which leaves the B part of the DAC for a future upgrade. The rest of the circuit down here is all to do with the switching, the gain switching for the precision op amps, so we get the range of voltages that we wanted from 0 to 10 volts, and that's something that I discussed earlier in the block diagrams. So I won't go through all the detail of that. Suffice to say that the output from the 12-bit DAC coming out of pin 14 is fed into the first precision op amp on pin 1, and then the output of that comes from pins 5 and 6, which can then either be fed through a second precision op amp, or it could be switched through to the output stage. Now, on the output here on the switching IC U6, you'll see the last 2 switches I'm using there to switch the output voltage, reference voltage, either on or off. So as the voltage is coming in on pin 10 of that IC, you see there the switch is initially open, so nothing is coming out, and at the same time the other switch in the IC is closed, which is grounding that point. So that means that when we have no voltage coming out, the output pin is grounded. We switch it on by sending a signal to pin 9, and that's coming from analog pin A2 from the Arduino Nano. And in fact I'm using all of these analog pins on the Arduino Nano as digital output pins. So that sends a signal to A2, triggers the switch there between 10 and 11 to turn it on. That supplies output there, and at the same time disconnects the ground connection. Now the point I would raise about these analog switches are that the type of switches we've got in there are break before make. So just a fraction of a second before we make the other switch, the previous switch opens. So in this case the earth switch there goes open just before closing the on switch between 10 and 11. And that also applies to the other switching. They're all a break before make switching arrangement. You'll also notice on U2 here on this switching IC, we've got some connections there we're not using at the moment, and I've outputted them to a socket, so we have them there available for a future upgrade. You'll see that all of the inputs to trigger these switches are coming from the analog pins which were used as digital output. The additional output pins here, A5 to A7, I've just taken them to a connector, so again they're available for any future upgrades should we wish. Now the TFT display, you'll see here that on that you've got the back LED there, and that's powered from the 5V supply, and initially I've put a 56 ohm resistor in there just to reduce the amount of current. But we'll have a look at that. We may increase that if we find the current is a bit high, but it should be okay at 56, but we could increase that to say 100 ohms, or you could even put a variable preset I suppose in there at some point. Now the connections going to the TFT from the Arduino Nano, remember I said earlier that the display, although we can supply it with a 5V supply, the logic level input and output for this I think are at 3.3V supply, and that means that we do need some form of level shifting between the 5V level output from the Arduino Nano to the 3.3V level of the TFT display. Now there's a number of ways of doing this. You could use this ICs that are able to give you the level shifting. You could use a combination of resistor dividers. You could use some Zener diodes and resistors. There's lots of different ways of shifting the voltage level. But I found in practice a very easy, simple and cheap way of doing it. As long as the direction of the information is only one directional, then we can use 10k resistors. So you'll see here I've simply put a series resistor of 10k in the signal paths where the information is coming from the Arduino Nano to the TFT display. When it's coming back from the TFT display at the lower voltage levels, we don't need any resistor, so I've just simply connected that. There's one there at D6 and one there at D12. So you see there D12, which is the master input slave output, so we're sending a signal from the slave, which is the display, to the master, which is the Arduino Nano. Then because the signal is going back that way, we don't need the level shifting there. We don't need to put a 10k resistor in there. And I found in practice that that simple arrangement does work quite well. We could at some later stage have a look at some other options, but it would mean that you'd add additional components and additional cost to the project. So let's just see first of all how that performs. D1 and D0 are not being used at the moment, so I've just taken those two pins out to a little socket, so they are available there for any future upgrades. So there we have it. Oh, just at the bottom here I've also got a 4-pin plug there with all the power supply connections on. Again, that will make it easier as we add any future upgrades to this project. We're simply plugging our power supply needs onto that little socket there, which gives us ground, plus and minus 15 volts and plus 5 volts. So there we have it. There's the overall schematic for our project today. So now let's have a look at assembling this and testing the project itself. For this project today I've designed and put together a single-sided printed circuit board, which you can see here. And because it is single-sided, there's a number of links on there on the top side of the board. I will make the artwork available to you so you can download it and then you can print it off and make your own transparency to produce your own PCB if you wish. But equally you could actually build this project on some matrix board if you wanted to. Now the other things that we're going to need for this project, I'm going to make both the Arduino Nano and the display pluggable, and I've decided for that I'm going to use some of these little inline connectors here, and again I'll give you details of that in the parts list, which you'll be able to download. And I simply just cut these to size and then fit them for the Arduino Nano and the display. The next thing we're going to do now is mount all the components, and then I'll come back and show you once I've soldered them onto the PCB. Here we now see the PCB with the components mounted. I haven't installed the ICs yet, or the Arduino Nano, or the display. They're all pluggable, and I think the best thing to do is we test the power supply before we plug anything else in, and we'll do that shortly. But there you can see I've got the inline connectors there for the Arduino Nano, and there's the inline connector for the display. Because they're both of the similar height, we'll probably have to just extend the height of that socket for the display, just so the display doesn't hit the Arduino Nano when it's plugged in. But my intention is, when we've finalised the project and put it in a project box, we'll probably have a flying lead coming from the socket there to the display on the front panel, and for that what I'll be using is probably a lead like that, which is one of these 2-point cables where you've got a male and female at either end, and that will connect the display to the socket here. If you wanted to, you could still plug the display in there, and for that what I would then use is some extension sockets to plug on top of the display socket there. And what I've found is these, where they've got some extra long pins there, and they would then simply just plug into the socket on the board, and then the display would then plug into that. So that would make sure it stands proud of the Arduino Nano. So that would just raises that socket to a larger height there. So the Arduino Nano, the intention is that that's going to be plugged in that location there. And then if you've got the extension socket there for the display, then the display can then be just simply plugged in into that socket. Socket there. Alright, just unplug that for a moment. Now the ICs on the board, I'll just quickly cover that. The socketed ICs, the one there next to the Arduino Nano is going to be the 12-bit DAC. The 8-pin IC there next to the preset is the voltage reference IC. The one below that is one of the precision op amps. And these two 14-pin sockets here are for the analog switching ICs, and then that one there you'll see next to the capacitors, that's going to be the DC converter IC, and then finally this one here is the second precision op amp in the output stage. So you can see there on the board you've got the voltage regulators around the edges there. Right, well, I have the unit now with the power connected, the 18 volts DC power connected. I'll just check that on the meter first of all, the voltage is going in. To remember, I've got that blocking diode, so actually what's going to the regulators is either side of that, so there is a drop on the blocking diode, so it's 17.48 volts going to the voltage regulator. So let me check the 15 volt supply first of all, and one of the easy way to do that is to go to one of the IC sockets for the, let's say, the op amp, and if I go to pin 7 of the op amp, I should be able to check the plus 15 volts. So let's have a look at that. I'm now connected there to pin 7, it's reading plus 14.85. That seems okay. And what I'm now going to do is check the 5 volt supply, so I can go on to the socket for the 12-bit DAC. If I go there onto pin 1, which is the power input, and there we're getting plus 5.02. So that looks fine. So what I'll do now is I'll plug the DC converter IC in and see if we get our negative voltage. We now have the DC converter IC plugged in, so let me now just check the negative supply, and I can easily get access to that if again I go to the op amp, and in this case if I go to pin 4 we should actually get the negative voltage. And there you can see I've got a minus 14.16. Just check the positive side again, and that is plus 14.85. So just a slight difference between the two, but I don't think at this stage that's critical, but so we'll see how it performs. And just finally double check the 5 volt supply plus 5 volts, so it all seems normal. So what I'll do now is I'll plug in all the other ICs. Right, well I now have all the other ICs plugged into the board, so let's switch on, and this time we'll check the reference voltage of 4.096. So I think I can get access to that on pin 13 of the DAC. And it's reading at the moment 4.101. So let me just see if I can trim that. There we have it set at 4.096. So the next thing we'll do is we'll plug in the Arduino Nano and the display, and then just see how it's working. I've now got the Arduino Nano plugged in and the display plugged in, and we'll switch on and just see if it's working. I've loaded the software already into the Arduino Nano, so hopefully we should see something. And I've got the meter connected to the output of the reference. One of the things with these displays is that they're upside down, so I need to turn it round. Just a second. I've finally got it the right way around, so at least we can see it correctly. There you can see the display, and I've laid out the display so we have the voltage reference that we've selected in the center there, and we have 3 options at the bottom there. We have voltage or set voltage, on off for the output to switch the load on and off, the reference on and off. So let's just touch the set voltage first. That will take you to a keypad, and let's type in 2.853, and then we press the set button. Now we've still got 0 on the output, so if we switch the output on by tapping on the on, and at the moment we've got 2.8532, more or less what we have there. On here is 2.853. So let's switch the output off again, and this time let's just set the voltage, and we're going to key in, say, 5 volts this time. If you don't have any decimal places, you just need to punch in the first number. So we've got 5 volts. Click the on button, and we've got 5.0034. So it's pretty close, actually. In fact, we can do some calculations later on the accuracy of this. And let's just try 10 volts. Let's switch that output off and see if we can get our 10 volt supply, 10 volt reference. So we got 10.0 set, and then switch it on, and we've got 10.0021. That's pretty good. I think what we'll do is we'll go through some further checks. Let me just switch off the load and go to the voltage set. Let's just go down to the lower voltages, so let's go down to 1.523, see how that responds, and switch the output on. I've got 1.526, so it's slightly out on the lower range by a few digits, but even so, to say we haven't done any real calibration on this, it seems to be working quite well. So I think the next step would be to have a look at doing some maybe checks and calibration, just see how it performs, but I think that will be for another day. Well, I think I'm going to leave the project there for the day. I think we've got a lot done today, and I hope you've enjoyed the design and the build of this DC Voltage Calibrator. What I will do for you in the meantime is I'll put you some links down below where you can download the full schematic for this project so far, together with the artwork for the PCB, and I'll also give a full parts list. In addition to that, I'll provide you with the version of the software that I'm currently using, but that may change as we progress. And I think for part 2 of this project, what we'll do is have a further look at the accuracy of this unit, check the sort of calibration, look at the possibilities of sort of putting this into a nice project case, maybe have a look at the battery option as well. I'm sure there's lots of things we can do to improve this, and we'll save some of that for part 2. And in the meantime, if you found this of interest, please give me a thumbs up and subscribe, and I hope to see you all again soon next time. Goodbye for now.